Hey guys, in this video we'll be discussing the Codeforces Round 868 that was rated for Dev 2. We'll be going through the first three problems, that is a characteristic, sort with step and strongly composite. So the very first problem states that consider array A which has elements from A1 up to AN, and the elements can either be 1 or minus 1. Now we define the A characteristic of this particular array as the number of pairs of indices, and obviously the pair of indices would lie between 1 and n, such that when we multiply these elements at the indices I and j, they should form a 1. Now it doesn't take a genius to come up with the fact that you'll only get a 1 when you multiply either 1 by a 1 or minus 1 by a minus 1, because the other way around, if you're multiplying a 1 with a minus 1, you're going to get a minus 1 itself, right? So we technically have to predict the number of ones we are going to have and the number of minus ones we are going to have. Although so before discussing how to do this, so then they're saying then what they're saying is that we have given you a value k, or they would be giving us a value k, and we have to define this particular array, or we have to construct this particular array in such a manner that the A characteristic, that is the number of pairs which at which the elements when they're multiplied gives us 1, right? So this A characteristic should exactly be equal to k. Now if it's possible to do that, then we'll predict the print out the array itself. If it's not possible to do that, then we'll print no. Cool. So now let's try to understand how we'll do this. Give me a second. Yeah, cool. So basically what we said is that the number of ones and the number of minus ones, right, would actually form a valid array. So the number of ones, so let's say there are 3 ones, right? So this one can be multiplied by this one can be multiplied by this one, right? Or in general, I can say that any of the ones, right, any of the ones can be multiplied by any of the remaining ones, right? So basically it's any possible sub array is what you can choose. I hope that makes sense. Or you can choose any of the 2 elements, right, from this. So how many possible combinations would be there in such a manner? There would be n into n minus 1 by 2, because any of these elements can be linked with any other element. So the total number of possibilities n into n minus 1 by 2. Let's call this, let's replace n by p because we are talking of positive ones. So let's replace it with p itself, right? Now what about minus 1? Let's say these are the number of minus ones are n itself, right? Because it denotes negative, so let's call it n. So similarly, the number of possible sub-arrays, or the number of possible pairs that we'll be able to construct in this form would be n into n minus 1. When we'll sum it up, they should equal to k. If we are able to come up with such a p and such a n, right, then it's valid. Now instead of n, let's just denote neg, because it's becoming confusing. So neg into neg minus 1 divided by 2. Now how do we come up with this p and neg? So basically p plus neg, this is the number of positive ones and this is the number of negative ones, right? P plus neg should be equal to the size of the array. That is obvious, right? So I can start with the value of p. I can brute force this up. So I'll check this value from 0 to n, right? If I have a value, let's say I for p, right? If the value of p is I, then the value of neg would be n minus I. That is obvious, right? And in this way, I can check for all the numbers. If I'm getting a valid solution, then I'll print it. Else I'll say it's not valid. So let me show you the code itself for this. So here's the code. What I'm doing is, firstly, I'm just brute forcing it up. So I over here is the number of ones, or over here, so as to explain it in a better manner, I'm saying that positive ones and negative ones, right? The way I explained it, if the number of pairs you're going to construct from positive and negative is equal to m, so if their collective sum is equal to m, in that case the answer is possible. So you'll say that the answer is possible, then you'll print 1 positive number of times and you'll print minus 1 neg number of times. After that, slash n and return. Else, if you reach this particular line, right, so that means no possible pair were detected. In that case, print no. Cool. Let's get to the next problem now. So the next problem is sort with steps. So the problem states that the permutation of length n as the array p of length. Okay, so that's firstly defining the word permutation. We'll not be going about that. But then they're saying is that we have been given with a permutation p of length k, of length n, and a number k, right? So what we are supposed to do is that we can shuffle any 2 elements, pi and pj, if and only if I minus j modulus. So basically the absolute difference between the indices I and j is equal to k. If it's so, then we can swap them, and we can do this particular swap any number of times. So there's no restrictions on that. After that, we have to say that, okay, after performing any number of such swaps, can we get a sorted array or not? Also, if you're not able to get a sorted array, then what we can do is we can pick two indices I and j. Now these need not be tied to this particular value. If we are unable to sort it, we can pick any I and j indices, and then we can swap it. But this particular operation of picking any two indices I and j, over here they have mentioned it, right? This can be performed only once, right? So they have mentioned that only at most one preliminary exchange can take place. Cool. And so then we have to print that how we were able to sort it. So 0 basically means that it was not even this preliminary exchange wasn't required to come up with the answer. 1 indicates that yes, one preliminary exchange was required to get a sorted array, and -1 would say that no amount of preliminary exchange, not no amount, but yeah, in a single preliminary exchange, you were not able to come up with the answer. Cool. So let's try to understand how to code it up. Or firstly, let's go through the logic itself. So let's say this is my array, right? Cool. Now, since they're saying that we can swap two indices if they are linked by a distance k. Now let's say over here k is actually 2. So I can swap this with this, right? I can swap this with this and this with this, right? And then for the other part, I can swap, let's say with green, I can swap this with this with this, and okay, there's nothing left. Cool. So what we're able to see over here is that since we can swap any of these elements, so let's just call this x1, x2, x3, x4, right? So x1, x3, x2, x3 and x4 can be swapped in whatever manner I want, or I can say that I can wholesome swap it. So what do I mean by that? So even if I want to bring x4 at the first position, or not at the first position, yeah, at the first position itself, I can do that, right? So x's, or the element x, x1, x2, x3, x4 can be swapped in whatever manner I want. Similarly for y, so y1, y2, y3, y4 can be swapped in whatever way I want. Now over here I had taken k as 2. If I had taken k as something bigger, let's say 4, right, then this number of x and y would have increased. So let's say this was x, and so the next number or next cell it would be connected to would be at a distance from 4 from this. So this is 1, 2, 3 and 4. This would be connected to this, and this would be connected to somewhere over here, correct? So if this was x2, this was x1, this was x3. Similarly, you would have something like a y1. It would be connected to a y2. It would be connected to a y3, which doesn't happen to be there in this array. Similarly, you could have a z1. This would be connected to a z2, and z3 is also not in this array. And let's call a a1. This would be connected to a a2. I hope this makes sense, right? So basically, all these elements can, so all the x's can be individually sorted, all the y's can be individually sorted, right? So how is this beneficial for me? So in the sorted array, right, since we are talking of a permutation, in a sorted array or in the final array, it would be 1, 2, 3, 4, 5, 6, right? It would be in the sorted fashion. This is what we want to achieve, right? Now, if I perform the similar operation over here, right? So I can say that, okay, these were interlinked. So let's say over here now k is 3. Just taking a random value, you can take anything. So basically these would be connected, right? Similarly, these would be connected, and similarly these would be connected, correct? So now if I rewrite this connected components, then I get 1 followed by 4, right, and then 7. I also get 2 followed by 5, right? I also get a 3 followed by a 6. So these are the 3 arrays I get. Now in the initial array, right, in the initial array, the same thing should be applicable. So what do I mean by same thing should be applicable? So basically in the let's say this was the initial array, and so initial array would also be of the same okay, it would be x1, x2, x3, x4, x5, x6, whatever, right? So after performing the same operation, I made them into different buckets. So I made all the x's equal. So this was y, this was z, maybe this was x, this was y, and this was z, right? I also made them into same bucket. So I got x1, x2, x3. Also got a y1 and y2. I also got a z1 and z2, right? Now I'll sort them individually. So I'll sort this entire array. I'll sort this array. I'll sort this array. Now if this is equal to this is equal to this is equal to this, right? Then I can say a valid answer is possible, right? So if these are equal, then in that case, I'll say that, okay, no preliminary exchange is required and I do have the valid answer. But there's another case. Now, what if, maybe it's not possible to do it. So there could be some differences. So how do we come up with that whether a particular preliminary exchange would help me with the answer or not? The simple answer is that since number of preliminary exchanges or number of such swaps were limited to 1, right? So we'll just say that all the elements, so when we're comparing that whether these two things are equal or not, we can simply compare, and for all of these arrays, right? So let me draw that with different color. So I'll call this all of these arrays differently. So I'll start traversing over it, and whenever I come across an element which I'm not able to find in its corresponding array, I'll keep a count of that. All right. So let's say this was 1. I checked whether you have a 1 in this array. Let's say x2 was over here was 1 itself. So 1 got validated. Then I came to the next number, that whether 4 is there in this array or not. Then okay, 4 was also there. Then it also got validated. Then I came to the other number, that was 7. Now let's say 7 wasn't there in this array. So I kept a count of 1, that okay, one of the elements were missing. Similarly, now I go for 2. I check over here whether 2 is present. So yeah, let's say 2 was present. Then I go for 5, whether 5 is present. So let's say 5 was also present over here. Then I go to the next array. Now let's say over here I check for 3. Let's say 3 was present. Cool. Now I go for the element 6. Now let's say 6 was not present, right? So I'll increment my count and C will become equal to 2. Now over here you can see that if your count is exactly 2, that means only 2 numbers were not available. That actually means those numbers are in opposite places, right? So basically this number would be 7 that was missing, and this number has to be 6 that was missing. So we'll just swap these elements. Okay, that got a bit messy, but yeah, we'll swap these 2 elements. Make sense? So yeah, that's how we're gonna do it. Now let me take you through the code. And also, if you're not if the number of operations or the count is greater than 2, in that case, even after doing one preliminary operation, you won't be able to sort this entire array. So you'll anyway print -1. Now if I take you to the code, let me zoom it a bit. Cool. So what I'm doing is I'm keeping an actual array. I'm keeping a sorted array, right? And then I define 2 sets, right? So over here, the reason of using a set instead of a vector is that in order to search, it's really easy to search an element in a set, right? If I would have to search in an array, it would or a vector, it would take me order of n space. So that's why I'm taking a set. Cool. Now I would define 2 sets over here, temp and AC. So AC basically means the actual, right? Right. And temp is just there so as to populate the sorted. So sorted basically would contain that type of array wherein you saw we had 1, 3 and 1, 4 and 7, right? And then we had 2 and 5, I guess. Yeah, 2 and 5, and then we had 3 and 6. I hope you remember this. So this is the kind of array we'll get. Also on the other hand, sorted actual would contain the number of elements that are actually present in the array V. Cool. So this is the way of doing it. Firstly, I'm saying that, okay, for all of these numbers, I'm going to calculate. So I'm going to traverse through all the numbers. I'm going to populate these 2 arrays. I hope this is trivial and this is understandable. Then I have to calculate the number of cells that are different. So I'll traverse across the sorted array, right? And then I'll say that if a particular element in I, so if this particular element J, if it's missing, right? So if it's not present in actual, so if I find it and I'm being pointed to the end element or end iterator, that basically means the element is absent. In that case, I'll increment my defs. At the end, I'll check that if my defs is 0, that means the elements can be sorted without using a preliminary operation. If my defs value is 2, that means a single preliminary operation is required. Else it has to be -1. Cool. I hope this made sense. Let's get to the very next question, which is also the last question we'll be dealing with. So this is a bit related to mathematics, and it's not that hard per se. So the problem states that the prime number is an integer bit. Okay, so they are giving the definition. Let's not read that. Okay, the definition is a bit long. I'll just give you the gist of it. So basically what they're saying is that there's something called a strongly composite number. The definition for it is that uh, a strongly composite number has several divisors. Every number has several divisors, right? Then now the number of prime divisors and the number of composite divisors would be individually calculated. And if the number of composite divisors, right, are greater than or equal to the number of prime divisors, in that case, the number is strongly composite. For example, in case of 15, right? These are the divisor it has. So let's not include 1 because 1 is neither prime nor composite. Rest, the number of prime divisors over here are 3 and 5, correct? And the number of composite divisor over here is 15. So basically 15 would turn out to be composite, but it's not strongly composite because the number of prime divisors are greater than the number of composite divisors. Same would be the case with 6. But if you look at other elements, let's say 8. So 8 has divisors 2, 2, 2. So, or you can say it has divisors like 2, 4, right? Or rather you can say it like 2, 4 and 8, correct? Now in these 3 divisors, only 1 is prime and 2 are composite. So 8 would be strongly composite, right? Now this is what they have mentioned. Now they're saying that you are given with the array A, right? And you have to come up with the array B. Now the lengths of these arrays can be different. The only condition is that when you multiply all the elements of the array B, you should be coming up with the product that should be the product of the elements of array A. So the multiplication of all the elements of A should be equal to the multiplication of all the elements of B. Also, all the elements in B should be maximum, should be strongly composite, right? Our task over here is to maximize the number of elements in B, right? So how would we do this? Now this is a greedy question. Let me just show you the slight intuition required over here, or the basic logic. So the basic logic is that since I can represent any number in the form of its prime factors. So let's say this is my array A, right? So this is A1, A2, A3, A4, so on to AN, right? I can represent A1 as a as a multiplication of its prime factors. So I'll do that. So let's say it was P1 into P2 into so on, right? Similarly, A2 can be also represented in prime factors, A3 and all the way to AN, right? Now I can multiply them because I want the multiplication to be similar. And by doing that, I'll get basically something like this: P1 to the power maybe X, P to the power Y, so on, right? Pn, or maybe like P, I don't know, P theta or P phi to the value theta, something of this sort. So just using random variables over here. Now, why is this important to me? The basic observation is that if I have two numbers and both of them are same, so two prime numbers, both of them which are same, let's say 2 and 2, right? Now, why is 2 and 2 important? So 2 into 2 basically means 4. Now, is 4 a strongly composite number or not? So basically 4 has three factors, that is 1, 2 and 4. We can discard 1 since it's not a prime and neither composite. But 2 and 4 are here. So 2 is prime, 4 is composite, right? So it has the number of composite factors equal to the number of prime factors. Because of that, we can say that this is a strongly composite number. Strongly composite, right? Let's take another example. Let's take the example of 6. Now 6 can be written as 1, 2, 3 and 6. These are factors of 6, right? Now over here, 2 and 3 are prime factors. Only 6 is a composite factor. So over here, number of prime factors are greater than the composite factor. So it's not strongly composite. Now why is this the case? Over here also, we had only 2. Over here also, right? We basically had 2 factors, or it was like 2 to power 2. Still, it was not giving us the right answer. Over here, there are only 2 factors, that is 2 and 3, right? And we're getting the right answer. That is because if the number of prime numbers you are having, right? So if the number of prime numbers are identical, so by that I basically mean that whether you are having 2, 2 or 3, 3 or 5, 5, right? In this case, occurrence of 2 or more prime numbers can get you the valid answer. However, if the prime factors are not distinct, for example 2 and 3, in that case they won't get you a strongly composite number. Now if I want to prove it, I can basically say that if the when you'll write it down, so since we only be writing the unique components, so the unique factors over here would be 2, right? And then when we multiply 2 into 2, we'll definitely get a composite number, that is 4, right? However, over here, when we say number of unique factors, right? So the number of unique factors itself are 2 and 3. On multiplying it, we get a 4. Or sorry, a 6, right? So these serve as the prime numbers, and this is the composite number, right? So with this observation, we can say that for we can form a number with the 2 occurrences of same prime number or 3 occurrences of different prime numbers. I hope this makes sense, right? Now we'll just utilize this, but how would we utilize this? That is something I'll show. So I'll walk you through the code. Right? I feel that the code is pretty understandable. Okay, let's look at this. So basically what I'm doing is, firstly, I'm taking all the elements of this particular array. Then for all the elements, I have to calculate what all prime number it has, right? And for each of the prime numbers, now because it matters whether you have distinct prime numbers forming a particular number or not, I'll have to keep the frequencies of all these prime numbers. So basically this would be a prime number. This would be a mapping of prime numbers and their frequencies, right? Okay. So this is the standard way of calculating the frequency of prime numbers. I'm not going to discuss this. This is pretty trivial. You can try to dry run this. If you have a doubt, let me know in the comment section below, right? After that, I'll be having the frequency of all the prime numbers. Now the main motive is that if the frequency of any of the prime number is greater than or equal to 2, then I can use 2 occurrences of it, right? Or I can use pairs of it so as to form another number that is strongly composite. So I'll be doing that. Now let's say my C is basically, okay, I defined a characters or integer C. So this basically is, okay, let me get over here. Okay, this is the number of strongly composite numbers possible, right? So yeah, if it's greater than or equal to, if the frequency is greater than or equal to 2, then for all the pairs I can form, that would be f by 2, right? I can say that I'm going to form these strongly composite numbers. Now if it was modulus 2, it was like an odd number, so still one occurrence would be left. So we'll say that, okay, f is equal to 1, else f would be equal to 0, right? Now over here, we'll say that for all these numbers, right, which still remain, so there would be cases wherein f would be 1. So let's say for 2 you were having 3 occurrences, so you were having 2 2 2, and for 3 you were having a single occurrence, right? So you took 2 2s to make a number, but now you are still left with a 2 and a 3, right? So you can also utilize them. So I want to calculate the number of such pairs. So if I see there's a remaining frequency, I increment this integer, that is int, right? At the end, I can say that, okay, I'm going to combine all these ints, but we already said that if the numbers are not distinct, if the numbers are distinct, right? So in that case, at least 3 occurrences of each is required to so as to form a number. So I'll say C plus is equal to, or I'm adding, or I'm forming a group of 3 elements each, right? So n divided by 3, and at the end I'll print a C. So if we run it, we get a right summation over here. Yeah, that's it. And yeah, one more thing. So initially I was getting a TLE. The thing over here is that we are actually checking if a number is prime or not. Now this entire loop itself is going to take some time, right? On top of that, we are trying to, so this basically is a root in loop, right? Okay, root in loop. After that, okay, yeah, you can actually decrease it. I'm not sure if it's root in, but never mind. Okay. So after that, if you're again and again calling is prime function, then it actually adds to a complexity, right? So what I did for that is I made a sieve of size 10 to the power 7, and I stored all the prime numbers into that sieve. So sieve of Aristotle's was used over here. I hope you all know about that concept. If you don't, then let me know. So from the sieve of Aristotle's, I tried to get whether a number is prime or not, and that saved some complexity for me, and hence the solution got working. Cool guys, that's it for the video. Thanks a lot for watching it. Bye bye.